Salutations, Internet. Good time zone. So, we're gonna start off the series with some housekeeping. If you've been keeping pace with the videos as I've been releasing them, first of all, thank you. It means a lot to me. Second, you will note that it is now November. And as you can tell from my accent, I hail from the United States, which means that I will be partaking in the American holiday of Thanksgiving. Well, in the American Thanksgiving. I know that Canada has one. I'm rambling. Don't mind me. That means that I will want to spend time with my family and loved ones. And so, as such, during that week, I will not be posting a video. We will instead be coming back during the first week of December, but that will be short-lived because for the last 2 weeks of the year, I am, for the same reasons, not going to be posting a video for those 2 weeks. And for the first week of 2025, I will not be posting a video, again, citing the same reason. It will be 3 weeks of no video during the changeover from 24 to 25. After that, we will pick things up where we left off, and it will be just fine. So, now that that has been taken care of, let's turn our attention to the equation sheet. You will see that I have included... Ooh, green. Forgot that was green. You'll see that I have included the time of flight for the parabolic escape trajectory. And what was the other thing? Newton's method. This one. I noted that I did not have an equation set for Newton's method, which I guess I don't really need, but it's my equation sheet. I think it's nice to have. Speaking of equation sheet, I think I will be able to post. I will be taking that time to look at finishing up and including my equation sheet on every video that I've posted so far. So be on the lookout for that. And then I can stop thinking about it. So, without further ado, let's get into it. So, by the title of today's video, you can see that we are going to be talking about time of flight for hyperbolic escape trajectories. Now, my notes just flat out give me the equation or the equation set for them. It's not a big deal. We did that several times throughout my class, and then we talked about them during the class. Not a big deal. I usually go to my textbook and I will find the derivations. So I did that, as I have for all of the other times that this has happened. And my textbook says, here's the equation. If you want to know more about it, reference this other textbook. But I don't have that other textbook. So I do not have the means to... I don't have the time to go looking for it and derive it myself. So we're going to try a slightly different approach to this, and hopefully it works well enough. So we're going to hop over to here, and I'm going to do a comparison. So we have our closed loop, equation set for time of flight, and for that, I'm just going to go ahead and write them in. All right. I hope you enjoyed the sped up video. Now, with that in mind, we're going to look at our, I don't want to call them open loop because it's not a loop. It's, yeah, escape trajectories, and I will go ahead and abbreviate that. Those are going to be, this is called the hyperbolic sine. You will sometimes hear me refer to it as cinch, and I'm just going to go ahead and I'll hold off on the reasoning for that for when we get to cosine. You'll see why. That is... Ooh. Let's try that again. There we go. Square root of e squared minus 1 times the sine of theta over 1 plus the eccentricity times the cosine of theta. And the hyperbolic cosine, or cosh, you see why I refer to it as cosh and cinch. That is eccentricity plus the cosine of theta over 1 plus the eccentricity times the cosine of theta. All right, so right off the bat, there are a lot of similarities. It's kind of like copying and pasting. There really is no difference between between the cosine and the cosine equivalent. And the only difference between the sine and the sine equivalent is that we have changed the order of this coefficient out here. And that is simply because we don't want to have a negative inside of our square root. At least as far as I'm able to tell. If we were to go through the derivations, I'm sure I can pull out a number of other reasons for it. But for right now, it's important to note that these are the exact same, except that this has the eccentricity and the 1 values swapped around so they can remain positive. To that end, we can also see that our time of flight, with reference to the periapse, is such. Similarly, over here, the time of flight from periapse is equal to the square root of minus a cubed. Remember that this is a hyperbolic time of flight, so our semi-major axis is negative. So our negative there is just to counteract it, or just to negate the negative, so that it can become positive. That cubed over mu, square rooted, times, and here's where it gets slightly different, at least according to my notes. The eccentricity times the cinch of f minus f. I apologize for the pause. I looked at my notes. I looked at my notes for the video, and I saw that I was missing a hyperbolic marker here, and so wanted to check to see if I had recorded it wrong, and indeed I did. The only mistake I will ever make, and I have successfully prevented it. Again, here we can see that the I don't know why I decided to write it like that. We can see that the time of flight equations are virtually the same, just that this section is negated from its counterpart. And the reasoning for that, I have decided, will be left as an exercise to the viewer. Or perhaps when I revisit this later, I'll talk about it. But for right now, just know that this is the opposite of this, and it is intentional. One last thing to cover, we have the radius, which for the closed loop, looks like this. And for the escape trajectory, it's gonna look like this, where it's virtually the exact same, except we're using, again, the hyperbolic cosine function. So I've used these equations. Actually, before I go too far, let me go ahead and box these in, just so I don't forget. These will be on the equation sheet that will be made available to you. So I've used the hyperbolic trig functions throughout this video so far. They're called the hyperbolic trig functions, and I've used them so far in the escape trajectories, but they are not, strictly speaking, trig functions. So as a bit of a refresher for everyone involved, we have, let's review, we have sinh of f, which is going to be e to the f minus e to the minus f over 2. We have the hyperbolic cosine, easy, hyperbolic cosine of f, which is e to the f plus e to the minus f over 2. And so, as you can tell from the graphic that I will put up on the screen later, thank you, future me, we have when our f value is positive for the hyperbolic sine, we have a positive value. When it is, because this goes to, this will go to 0, while the first term continues to grow to a non-zero value, an increasingly large value. So it becomes positive dominant. When it is a negative f value, this will reduce to 0, and this will grow to an ever increasingly large number as you move away from 0. For the hyperbolic cosine, you see that it is a mirror of itself. When f is positive, we have positive values because this goes to 0. And when f is negative, this goes to 0, and the negatives will negate themselves, and we still get positive values. Very nice. The hyperbolic tangent, or tanh, I guess, we're not really going to use that. That doesn't have as many, I don't think it has any applications in this topic. I could be wrong on that, but I did not see fit to write it in my notes, and while perusing the textbook, I did not happen to see it there either. Regardless, the hyperbolic tangent functions much the same as the regular tangent does, in that it is the hyperbolic sine of f over the hyperbolic cosine of f. And like I said, I'm not going to get into it too much, but I have it on the graphic on the screen so you can see what the tangent is doing, what the hyperbolic tangent is doing at the same time. Like I said, we're not really going to get into it. I'm not going to worry about it too much for right now. And that's pretty much all there is to that. Actually, so while we're here, we're talking about hyperbolic trig functions. So we have a method to plug in a theta and get out a sine of f, and then we can plug in a sine of f to get a time. But as you can see, we also need regular f. So if we want to extract our f value from the hyperbolic sign, let's go down here. So the hyperbolic sign of f, and I don't want to write that during this derivation, so I'm going to write it as v for value. It can be any letter, it can be q. It's not a defined letter. I just don't want to write cinch f 6 or 7 times. Right. That is going to be e to the f minus e to the minus f over 2. Except that's not super pleasant to work with, to try to backwards derive. Backwards derive? Sure, why not? So instead, we're going to write it as e to the 2f minus 1 over 2 e to the f. This is one of the alternative ways to write the hyperbolic sine function. Wikipedia, at time of recording, has 3. And if I can remember, I will also include a graphic of that just so you can see what they look like. But we don't really care about all the others at the moment. We are using, I'm just going to write that out. We are using this because it is easier to solve for f this way, is really why I'm doing it. So let me rewrite it. All right, so we will put everything on one line. We have 2v e to the f is equal to e to the 2f minus 1. We will then, I'm going to take that guy over to there. Really what I'm going to do is I'm going to have these two swap places. So we have e to the 2f minus 2v e to the f. And that is going to be equal to positive 1. All right. Why did I bring us here? Because this is getting dangerously close to a factorial, a FOIL product, really. No, definitely not a factorial. No, it is getting close to a FOIL product. And for that, to complete that, don't like any of those characters. Let me try that again. E to the 2f minus 2ve to the f. And then to round it out, we're going to add v squared to both sides. So we are going to add 0. 1 plus v squared. So adding v squared to both sides, one of the mathematician's favorite tricks, adding 0. All right. Let me bring it down to here, just so I have more space. And I'm going to write it as e to the f minus v squared. And let me check my notes to make sure that's right. Yes, yes it is. That is going to be equal to 1 plus v squared. We'll take the square root of both sides, so e to the f minus v is equal to the square root of 1 minus v squared. E to the f is equal to v, that's the square root of 1, that's supposed to be plus v squared. There we go. Woo! Again, the only mistake I would have ever made in this entire series, and I managed to prevent it. How great am I? Solving for f now. We have the natural logarithm of v plus the square root of 1 plus v squared. And actually, really quick, let me rewrite that. All right, so this is what it breaks down to when you take the v's and you plug them and you replace them with the hyperbolic signs. It is the exact same. And there you go. You have a method. You have an equation to use to convert from hyperbolic sign to f so that you can use it for this equation. Of course, if you have a calculator that has an inverse hyperbolic function on it, you can always use that. My calculator does. I just do this for fun. Anyway, I would like to thank everybody for stopping by. I hope you have a great rest of your day.